Hi, my name is Fernando Esteban, and we're going to explore a very important problem, air pollution.
Hi, my name is Ingrid, and we'll break down the science behind the problem and the solution right here on this video.
Hi, my name is Santiago, and we'll do it by exploring a creative solution using the specific properties of the pollutant themselves.
Hi, my name is Ana Paola. So, let's talk about air pollution. Air pollution is a mix of harmful substances in our atmosphere. We can group them into solid particles like soot, dust, and harmful gases. Today, we're focusing on five specific gases: sulfur dioxide, nitrogen dioxide, carbon dioxide, methane, and chloromethane. But why are these specific gases so bad? Let's break down their impact. For human health, pollutants like NO2 and solid particles can cause several respiratory issues, like asthma and other lung diseases.
To understand how this molecule behaves, we will look to the Lewis structure, the 3D shape, the polarity, and the intermolecular forces. The first molecule that we will see is sulfur dioxide. We can see the Lewis structure. We can draw it this way or this way. Then we can see in this way the 3D shape. We can see that it has two bonds and these long pairs. This is a polar molecule. And also we can see in this diagram that have dipole-dipole force and dispersion. Then we have nitrogen dioxide. We can see the Lewis structure. We can draw it this way or this way. Then over here we can see the 3D shape. We can see that its polarity is net dipole. Also it's a paramagnetic, which means that have an unpaired electron. We can see the molecular forces right here. It's a polar molecule, so it has dipole-dipole and dispersion. Then we have carbon dioxide. We can see the Lewis structure. In this molecule, there is only one way to draw the molecule. Then we have the 3D shape. We can see that its polarity is non-polar. And in this molecule, the only force, the only intermolecular force is dispersion, also known as London dispersion. Other molecule is CH4, also known as methane. We can see the Lewis structure. Also, we can see right here the 3D shape. This 3D shape is a tetrahedron. We can see that its polarity is non-polar, and right here we can read that the only intermolecular force this molecule has is dispersion. Then we have CH4Cl, chloromethane. We can see right here the Lewis structure, and right here the 3D shape. We can see that it's a symmetrical tetrahedral, which means that this chloride have more electronegativity than the hydrogens. And right here we can see that this molecule has two forces, dispersion and dipole-dipole. Then we have water, H2O. We can see right here the bond angle, and here we got the result of the acidic rain. Right here we have nitric acid, and right here sulfuric acid. We can see right here, like I just said, acidic rain. We can see the boiling point of nitric acid and the viscosity. Then we have the boiling point of sulfur acid, and then we have the viscosity of sulfur acid.
Here we can see that all the elements present in the acid rain present hydrogen bonding, all of them.
Thank you, Esteban. As my partner just said, we have two different pollutants. One with very polar and with high dipole forces, and another one not polar with weak London dispersion forces. These intermolecular forces affect our physical properties. If you have more charged molecules, it takes more energy to separate them. That's why all molecules that are polar and have higher intermolecular forces have higher boiling point, higher viscosity, and are thicker. But most importantly, these forces allow us to use the dissolved light. We can use polar liquids in order to capture the polar gases, or use non-polar liquids to calculate the non-polar gases. This is the first step for our 3 basis step program. Step 1, electrostatic precipitator. First, we use an electrostatic field to remove all the solid particles from the air. Step 2, the water scrubber. The air then bubbles through water, and water is polar. So we use the light dissolved light, and we trap our polar pollutants like CON2, NO2, and CH3Cl. And finally, the step 3, the non-polar scrubber. Finally, the air passes through an oily non-polar liquid. This traps the remaining non-polar pollutants like CO2 and CH4. This targeted process allows us to systematically clean the air. Now Ingrid will now wrap it all up.
¿Ya estás lista? Sí, dale.
Existing technologies employ a philosophy of destruction. They use aggressive methods like intense heat, RTO, chemical neutralization, FGD, or catalytic conversion, SCR, to permanently break down and eliminate specific pollutants. The proposal employs a philosophy of management and separation. It is an nuanced approach, guiding pollutants based on their own properties like electrical charge or polarity, and sort them out in the air into manageable waste streams rather than destroying them.
So, as a conclusion, we as a civils, we have the responsibility to take action in these problems that involves all the society, applying all the content that we already know that are being surrounded by the chemical process that we can do, and having this responsibility not just by doing this project, but in the daily life, by applying solutions, small solutions that can contribute in small proportions.
Important to apply our knowledge in problems of the real life. This way we can improve our world and also improve our quality of life to all of us with the knowledge we know, applying the science in real life problems like our example of air pollution.
Well, for me, the conclusion is that after all this research and after all this investigation, is that pollution is a very big problem that we need to take care and find the way or the fund to involve all the persons in the world to solve it. We already have the knowledge and the science, so it's just to be compromised.
What you taught me is that it's not about having the strongest specialist, but having the perfect plan. Each step sets up the next one. So in these kind of problems, it's not about brute force, but about having